Hi, everyone. Welcome to another deep learning session. Thank you for joining us today. And before I tell you about our meetup, let me just explain you the format. For those of you who are not familiar, we will have around 45 minutes of talk, followed by 15 minutes of Q&A. So please use the YouTube chat to place all your questions, and we will ask them to our speaker in the end. So today we're very thrilled to have with us Gonçalo Faria. Gonçalo is a lead machine learning engineer at dotmoovs, and he's here to talk to us about the relationship between machine learning and causality, a novel topic in our sessions. So Gonçalo, welcome. Thanks for joining us, and please take it away.
I thank you for the warm introduction. So yeah, I'm going to speak about. I tend to convince you that many of the deep learning problems are intrinsically related with causality, and for that reason, I will also speak about causal discovery and how to recover causal relations from data. So yeah, I will speak about the limitations, give like a brief overview of causality and causal discovery, and then go into the work I did in my master's dissertation. So inherent to deep learning and machine learning is essentially the IID assumption. So we assume that the data comes from independent, identically distributed, and also essentially there's like a hidden distribution which is giving us data. We only observe the samples, and we want to make systems that are able to generalize to other samples from the same distribution. So if we have a predictor, we want the predictor to be good on the data that we have, and also other samples from the same distribution that we haven't seen. But that, as you might expect, since reality doesn't follow these assumptions, right? So reality is like a non-stationary process, right? Where the distribution is hidden, but it's not fixed. It might change as time goes on. We have to deal with it in somehow, right? And generally, there's something related with I'm showing here is what we do in practice, I guess. So there's like one part where we do the model training, right? And then we enter into this loop where we are doing monitoring and fine-tuning. Obviously, depending on the task, this might be not as frequent, right? But we are looking for instances of the model behaving badly as data comes in. We have like a trigger, some moment where essentially we take the data that is out of distribution or the new data, and we fine tune our model again, and we repeat the process. So this assumption of identically distributed is like a mathematical conception that we use to make beautiful algorithms. In reality, what we have is like a multi-agent system where each agent has its own policy and its own goals, and it interacts with our model as well. So our model is just one agent, a special one, and especially for decision-making problems, this is really important, right? Because just because we deploy a model in the system, and if the model is controlling the system, so if it's like let's say Twitter and it's banning Twitter users, or if it's Google search and it's recommending based on the website's characteristics, essentially just by the fact that we deploy the model, there's like an instance data drift, right? So essentially, while we are testing our model using a test set data set, which is IID from the same distribution as the training set, this is in reality, this is not what we want, right? We want a model that is also good for a slight shift in distribution, because that's what actually the model will see in real time. So I guess a good idea would be to have like an extended definition of generalization that would encompass this, right? And deep learning, I guess, doesn't deal with that with this for now. And so that's why we need this iterative loop of always trying to fine-tune the model to new data, at least for some applications. And also there's the limitation of interpretability and scientific understanding, right? If a biologist is trying to figure out the relations between its covariates, looking at cells and things like that, probably, just fitting a machine learning model by itself won't give, understanding of the underlying system, right? If we want to do figure out if a particular treatment causes the recovery, if it cures a patient, just fitting a machine learning model to the data, it won't give us an answer generally. It might assist in the sense that we might make a good simulator, but in the end, the interpretability and scientific understanding is not in the deep learning part, which is like it's a limitation. So this gives us this brings us to the point of how can causality help with this, right? So there are many benefits for using causal predictors. When here with causal predictor, I mean like, okay, we have a model for, let's say, a predictor for variable y, and I only look at the covariates x, so the features x, which actually cause y, right? And causal predictors are optimally robust in the sense that if I have like many environments, here denoted with E, and these environments are the ones I observe. They are a subset of the entirety of the environments that there could be, right? If I have like data from these environments, the causal predictor is the one that minimizes the loss on the worst case environment, right? So if you assume that if you want to have like this robust model that's really good, even especially for the worst case environment, right? When some people are changing, you can use the causal predictor. And so causality is inherently connected with prediction in heterogeneous scenarios and environments. Hence, it's a good approach if we want to avoid having to do all the fitting, the fine tuning, right? Okay. And also the causal factorization, is also the one that adapts faster. If you have to adapt it to new distributions, to transfer distributions, the causal factorization is the one that adapts faster and with fewer samples. So here I have a plot of the log likelihood, right? Higher is better. And what we see is that, so I have two variables here. So it's AB, and the ground truth model is A causes B. And if I have to have like so I could train this, I could fit like a distribution, a joint distribution for these two variables, right? And I could choose two factorizations. I first have a model for a distribution of A, and then the conditional V given A given B, or I can do the opposite. I can do a distribution for B, and then the posterior V given A, right? No, A given B. And so if we have the causal factorization, if there's like an intervention, like a change in the model, if we have the correct causal factorization, we need less data and it's faster. So as in the example I showed you before of the fine tuning, you'll need less data. That means that you can iterate faster, which is also a great benefit. So what should I do if I don't know the causal model, right? I want to use causality, but I don't have information about, in my tabular data set, let's say, what causes what, right? So let's consider a problem where you see that there's a correlation between so data set where you have a correlation between going bad with shoes and waking up with an headache, right? Does this mean that there's like a cause-effect relation here? No. So does going bad with shoes makes one wake up with an headache? Obviously, as you learn, correlation is not causation. But you would be surprised how many times people assume causation when they see, even in papers and journal articles, when you in the media, when they see this association, right? Especially when they have an hidden interest of proving that you shouldn't wear shoes when you go to bed. But in this case, I have the main expertise, and I give you that there's a hidden confounder. The confounder essentially is giving this association between these variables, right? Because it was hidden, and essentially there's like the variable is drinking alcohol. So drinking alcohol causes both going bad with shoes and waking up with an headache, right? So if I didn't know I had this variable in my data set, these two variables would appear related, and I wouldn't be sure which one was which, right? So what was the causal direction? But also it shows also the issues with doing causal discovery, because there's like these limitations or I guess we have to make methods that deal with it and confounding, right? Okay. So what's the idea of data-driven causal discovery? Okay, I have this data set and I apply some computational method and I recover this cause-effect model where the arrows indicate cause-effect relations, right? So the arrows going from drunkenness to headache, it means that drinking causes waking up with an headache. Unfortunately, this is a really complicated problem. By using observations alone, we can only identify these independent statements. For instance, that going bad with shoes is independent from waking up with an headache, given that I know that someone drank, right? So, and only with these independent conditions, there are a plethora, there are many causal graphs that could originate them, right? One of them is the one I told you before, right? The one that I'm saying is the correct one. Another possible one is I woke up with an headache that caused me to drink, and then it caused me to wake up with the shoes. And also I woke up with shoes that would cause me to have an headache, which caused me to drink, then have an headache. Of course, and these three causal graphs together, they form what is generally called the Markov equivalence class. So this class of graphs that could, given some observational data, you couldn't distinguish them just by conditional independence alone. Okay, since in this case you can have the temporal information, right? In this example, you know that you can't the causes can't go back in past. So one event that happens now can't cause something that happened in the past. If with that information you could actually prune the number of solutions here, but obviously we won't assume that for now. We don't assume that, and so we will do a general assume that these variables don't have this information. Okay. So what's the solution? So in science, there's already many scientific knowledge which has causation. So what we've generally done is raise hypotheses, do experiments where we have a controlled scenario where we intervened on the data generating process, and using these interventions, it's possible to actually discover causal relations. In this problem specifically, an intervention would be something like forcing people to drink or not, right? So selecting a bunch of candidates, forcing them to drink or not, forcing them to go to bed with shoes or not, randomly, and provoking headaches randomly as well. So if I collected the data set in these scenarios, right? If I had data for each of the conditions, including the observational one, it would be possible to distinguish cause-effect relations, right? We would be able to make methods that are actually, they can distinguish them. I wouldn't have the same issue of having the Markov equivalence class. But as you might guess, it might be complex, expensive, and sometimes unethical. Okay, so structural causal models. How do we relate causal statements with probabilistic ones? Because we need probabilistic ones if we want to do machine learning models on top. So I guess this is sort of it will be our representation of the system of interest. So we have a set of equations, right? So and these equations don't have equalities, right? They have assignments. So you should see this as lines in programming code, right? So the first one is x1 in this example, x1 equals to a random noise. Then x2 equals a function of x1 plus random noise, and x3 equals a function of x1 and x2 plus a random noise, which is Gaussian. So the idea is that given these equations, we build the graph of dependencies, which is sort of a computational graph where the variables on the right side link to the variables on the left side, right? And this obviously this graph can't have cycles, and we can obtain the distribution for this graph as follows, right? As the distribution on the right, which is essentially the conditional distribution of the child given the parents. Obviously, you could have multiple factorizations, right? But here we will like give a special treatment to this one because it's the one that most better represents and condenses the information on the graph. And since this is a causal model and not just a Bayesian network, will be able to manipulate, do manipulations on the model. And these manipulations will be called interventions, right? So one example of doing a manipulation and intervention is going to the second equation, the equation for variable x2, and we'll force it to be equal to 2. So we are essentially changing how the system behaves. As you see in this graph, in this model, there's no longer a dependence between x2 and x1, right? So I have like the source causal model, and I can do interventions on them, change them slightly, and I then get new data sets for these interventions. But as you can see, most of the models stays the same, right? I only change a part of it, in this case for x2 equals 2. And then the distribution for this model appears on the right. So essentially, it's the same idea. I have the child variable given the parent variable, but for the variable x2, I have a different distribution there, which entails that I did some intervention. I changed the process. Generally, I'll use this do notation by Judith Pearl, which actually represents this. It represents changing the data generating process, and in some way, right? So, and this x equal to 2 shouldn't be interpreted as conditioning, right? Because when we condition on a system, we are essentially filtering the values of the distribution, right? We are saying, okay, given that this variable has this particular value, what are the values of the remaining variables? But we aren't doing this. Here we are changing the system even to a state that might never appear in the observational model. Okay, so this is like the conceptual framework, right? You could assume that you can have arbitrary complex assignments with neural networks inside and things like that. And also, each of the variables might be multidimensional and not unidimensional. Okay, if I were to sample from the distributions I showed before, and then do a scatter plot, a pairwise scatter plot. So I essentially plot the pairs of variables. I would have, in gray, the observational distribution, right, without the intervention, and then in blue the intervention distribution when I force x2 to be equal to 2, and as you can see like a constant function in x2 equal to 2, and the remaining variables, they still have their some amount of noise. So the idea is that there is a lot of commonality in these two distributions, right? But obviously, I'm changing the distribution in general and the samples just by the fact that I changed the system. Okay. So for causal discovery, and if you are using only observations, you essentially will always have this problem that you can only find one of the solutions for your problem, right? Or one of the elements of the Markov equivalence class. And there are many methods for doing that. Some are constraint based, where you do independence testing, and with that you get a bunch of constraints of the graphs that cannot be, and then you just find the ones that satisfy. There's like score based, where I define a score that is able to identify. So I score graphs, and I'm able to identify the graphs. So you prove that you can identify the graphs in the Markov equivalence class. There are hybrid that sort of use both, and there are many others, especially now with the deep learning community trying to propose methods for solving this. Okay, so the simplest method you could do for using deep learning and trying to recover causal graphs is so you essentially have to search over the space of graphs, and this is generally done using a continuous relaxation, where instead of doing the search over the graphs, you do a search of the parameters of a distribution of graphs. Essentially, you have these parameters. The distribution you can parameterize in many ways, but you have to ensure that there are no cycles, because this is a tag, right? And also you have to ensure that you penalize dense graphs, right? Because if you just optimize this without penalizing dense graphs, it will just try to find a fully connected graph that better matches the data distribution. And there's like also a likelihood where you try to find the parameters that maximize the likelihood given some specific graph. And this is implemented essentially with the autoencoder, where you can see this as a form of dropout where you are masking the inputs, right? So essentially you have for each, so you are trying to predict each of the variables, A, let's say, A, given all of the variables, right? A, B, and C. Obviously, we'll be masking the inputs. So essentially there won't be cyclic dependencies. So you will never be able to use A to predict A, right? But essentially the graph will be controlling this part of which samples do you mask, right? And this is tricky because since you can't have loops, if you leave you can't just leave everything open, right? In terms of what information passes. So essentially this you make a distribution over, and this essentially is a reconstruction loss. And this is how you could do this. Yeah, and enforcing the cyclicity, it can be a constraint. It can be inherent to how you define the distribution, right? You could do like sample permutation matrices multiplied by triangular matrices, and you ensure that you always find the DAX, right? Okay, and so as I was showing before, right? So you can see this as having a neural network which gets all of the inputs. But you have this G control, which is a binary variable controlling the links. So if when it's 1, essentially you let the information pass. When it's 0, it doesn't pass. So essentially you define the model in this way, right? And you try to train on reconstructing the input. And this can also be seen as doing lasso, but now instead of so a lasso is the one you try to predict the variables, and you try to use L1 regularization. But here you essentially you make sure that the dependencies are acyclic, right? Okay, doing causal discovery with interventions. If you use interventions, as I said before, depending on the number of interventions, you can essentially guarantee that you will find the correct graph. Obviously, you would have to still penalize the dense one. So, because if you don't penalize the dense one, it will always be the fully connected one. But still, essentially, the idea is that you have these different data sets, right? Here denoted by K, right? So different sets of data sets. And then you try to find only the parameters that differ in the intervened variables. So let's say in the dataset 1, the first variable was intervened. Dataset 2, the second variable was intervened, etc. So essentially, you have like lots of commonality. Lots of the parameters are the same, and some of the variables are different. And for the variables that have different assignments, you have like a different parameters denoted by theta k, which essentially will only have to worry to fit the model in the assignments that were changed. And in general is sort of the same approach, right? You have to make sure that they are cyclic, and also penalize the dense graphs. Okay, I guess, and this takes us to the work I did in my thesis, right? So we considered with André Martins and Mário Figueiredo, we considered differentiable causal discovery under latent interventions. So we consider a new scenario, right, where we know we have a big data set where there are already data collected from these interventional regimes. However, we have a mixture of interventional regimes where we don't have information about the correspondences. So we don't know for each sample from what regime it came, so from what intervention it came. And also, we don't know what are the particularities of each intervention. So did this intervention altered, let's say, did this intervention force people to drink? Did this intervention force an headache on someone? And so we don't have this information, but ideally would like to use this heterogeneity to help us identify the causal graph in a better way than just the observational case. So we first tried to make a model that was able to recover latent interventions given the correct causal graph. So we proposed like this model, which is like an infinite mixture of intervention structural causal models. And then we defined the prior distribution for the interventions, which was a Dirichlet process. We did this just to make sure that we weren't imposing the number of clusters and the number of interventions. Okay, so we do a few assumptions in terms of factorization, and essentially this problem can be seen as trying to find the posterior over the assignments. So we want to know for this sample what's the intervention it corresponds to. We do use variational inference because it would be intractable to do it analytically. And so this can be seen as sort of a clustering problem, where the clusters have just a few degrees of freedom. So essentially, they have a lot in common. The only thing that changes are the assignments of the intervened variables. So it's supposed to be slightly easier than the normal clustering problem. So here I have an example where in red I have the observational model, which you can see as being like a line, right, with noise. So a Gaussian with noise. But then I have the interventional distributions which lose the dependence, so they are just constant for one of the dimensions. And this overlap becomes even more noticeable as you increase the number of dimensions, because while here it's all two-dimensional data set, so if you do an intervention, essentially you break the dependence. If you had like 100 variables and you only change 2, the data set will be like highly overlapping, right? Super similar. Okay, so I guess we propose this variational autoencoder architecture, where essentially we are trying to predict this distribution over assignments for each x. Also, we try to predict the variational posterior for the interventional variables, which is noted here by Q m tilde. And then we have like this model, which is essentially the evidence lower bound of the likelihood of the evidence. Okay, and then we try to train this on the reconstruction loss. Okay, so the results, essentially, we have lots of experiments, even more that they are shown here, but for the experiments with single node interventions, the key takeaway is that we get really good results in terms of finding these clusters, right? For most of the scenarios. And different types of graph sparsity and different types of number of variables. Essentially, it works pretty well. And we don't show here, but I don't show here, but when you compare with like vanilla clustering methods, we actually overperform. So yeah, so we get better results than just using k-means and Gaussian mixture models, as you would assume, since our problem is way easier. So can we both do the latent intervention recovery and the causal discovery? And the idea, the formulation is sort of the same, but we replace the likelihood by our elbow, our evidence lower bound. So essentially, we are approximating the score used in causal discovery with interventional data, and this approximation will be as good as our variational approximation, which we try to maximize. So minimize the difference. Okay, so essentially we are trying to do both. So we have we are trying to find the parameters of the graph distribution, and then at the same time trying to find the parameters of the approximate posterior, and then of the model as well. So it's sort of a traditional operational encoder architecture. Okay, and this sort of introduces many variants. It sort of generalizes a class of possible methods of causal discovery. One is the latent one, which is the one we are introducing, right? We don't assume the correspondences to interventional regimes, nor the experimental conditions. Another is the unknown, which is already done, where they assume the correspondence between samples and interventional regimes. So they know the partitions. They know how to partition the data set into distributions, but they don't know the experimental conditions. Another variant is the known one, which is the vanilla interventional data case, where they know the experimental regimes, and they know the correspondences. And another is the observational one. We don't assume interventions. And another one is a semi-supervised version, where essentially for a fraction of the samples, we know the correspondence to interventional regimes. And also we don't know the experimental conditions. So in our experiments, we first started with cause-effect pairs. So essentially, we had the two variables, A and B, and either A caused B or B caused A, or they were independent, right? So in these bar plots, we have essentially the four scenarios, right? The experiments for the four scenarios. One is the unknown, the known, the latent, and the observational. So Hamming distance essentially is a metric that measures how far our prediction is from the ground truth graph. So the blue means that we are essentially equal. Our prediction is perfect. One, it means that we had one edge of difference, and two, we are completely wrong, right? Remember, only two variables. So what we can see is that the unknown and known variants work pretty well, as expected, right? The observational one is really bad, right? Because as we know, just by correlations, we can distinguish cause-effect relations. So as expected, it worked really bad. But the important part here is that the latent one, or the method we propose, is actually able to be significantly better than the observational one, and is actually able to recover more cause-effect relations than the observational one. Each of the experiments essentially was sampling 60 graphs and doing the averages to obtain this, and this is an histogram. So yeah. So we then tried to do with a slightly more challenging problem, which was 10 and 20 variable problems. Here is only 10, but okay. So 10 variable problems with different levels of graph sparsity. So the main takeaway here is that this sort of pattern appears always, which is we essentially overperform the observational one. We are slightly worse than the unknown, and we are way far away from the known versions. So this means that if you are in a problem where you don't have international data, and you know that you have heterogeneous data in your data set, if you know that someone intervened on your system, then showing our model is actually pretty good in the experimental data. And also we can see that, for different types of problems, the gap between latent and unknown starts to shrink, right? It is not always clear that they are so super far apart, right? But generally, it's always worse because, of course, in the unknown, we have significantly more information. We also tried our data sets on a really popular and controversial causal discovery data set, where essentially this is like a problem about proteins from biology. And there's the ground truth consensus graph, where a bunch of scientists, through time, they developed the causal relations of the underlying model. This problem has lots of interventions. If in this figure you can see like this blue, this red and green parts, right? These are the interventions. We have this information, and most of the methods in this table, other than ours, they use this interventional information, and they have methods for dealing with interventional data. And what we show here is the first column is Hamming distance, and what we see that our method is competitive, and arguably it overperforms. And also you can see, F1 score, it has good results. And most importantly for us is that it has a really low amount of edges in the reverse direction. So it sometimes fails, but when it fails, it doesn't fail in the reverse direction. So it doesn't say, okay, the cause is the effect, right? So, and in that sense, it sort of overperforms the remaining methods. And obviously this was a bit, we weren't expecting these results, because we were expecting obviously that the methods that use interventional data would be better. But as I said, this data set is controversial because the community thinks that the experiments were not well performed, in the sense of the biologists that did experiments didn't annotate correctly the interventions, and also there might be loops and feedback loops that are also making things worse. But so that means that the other methods might be using wrong information, right? Allegedly. And so our method, fortunately, can deal with this, and seems to show that if we ignore this information in this specific problem, it helps. Okay, so in conclusion, make heterogeneity and non-stationarity your friends. So if you have a problem when you want to discover cause-effect relations, you can use this information and assume that you have latent interventions and use it to discover cause-effect relations. And while we in general, while we can see some scenarios and applications where assuming latent intervention might make sense. Let's say that you are doing A/B testing, right? And you just forgot which users were subject to what test, right? And you want to discover the cause-effect relations in the problem in your system. And in that case, you can use our method, of course. The method of you want to understand the cause-effect relations might be in the past, so you can't go back into interventions. The method might be in the future, and you can't go there and make interventions. And you might have just some cue that there are interventions in the system. There are external parts of the system intervening, and you want to use that knowledge. Let's say that you know that COVID happened, and that was like disturbing to a particular system. You can use that as a signal for causal discovery. Yeah, but in general, we are more worried. We are more defining a method for this heterogeneity scenario where you have like a big data set where from different locations and times, and you just assume that there are latent interventions and try to figure out the cause-effect relations. And we sort of show that it's a good assumption, I guess. So yeah, that's it.
Thank you, Gonçalo, for your presentation. While we wait for some questions from the audience, I have a question in our last slide. So what is the most common situation where you can apply these techniques? It's like you know that some interventions have happened, but you don't know what, and you want to extract the cause-effect relations?
Yeah, so if you have a data set of where you gather data across many environments, let's say, but you know that you have data from many environments, but you don't know the partitions, right? You could try clustering, right? But what we show is that like trying to find the causality and the clustering, it will give you better results. So if you just do one approach is just doing clustering, and then doing causal discovery with the international data.
So what do the clusters represent? The ones that you showed, is that intervention? Each cluster is an intervention?
Yeah, so it's data from the different interventions. So you go to a system, let's say it's a randomized control trial, right? You go there and you force people, you select a bunch of people, and you get this new data set, right? You select for a particular factor. Let's say you give treatment A, and you get data for that. And then you go there and you do treatment B, and you get data for that. You might, if it's like a more complex system, you might have many variables that you want to provoke, right? So, and you get an intervention is going there to the system and changing the data generating process in some way.
But like changing just one variable, or you can change
you can
different
change
variables?
many. I didn't show you, yeah, but you can change many. And the change might not be discrete, right? You might not just force it to be a particular variable. Let's say you have to take this treatment. It might be random, or you might just do a slight mechanism change where for a particular variable, you just change slightly the mechanism. So you actually retain the independencies from the variable's parents. So just perturbing the system somehow, right?
Yeah, but then you have the clusters, and how from there how do you extract like the variables in the cause-effect relation?
Yeah, so the clusters essentially will have a lot of commonality, right? Because it's all, so if you only change a few of the variables, the remaining system will still be the same, right? The remaining mechanisms, all the assigned values in this system, they will remain intact. So there's a lot. They are special clusters because they have just a few degrees of freedom. They have a lot of commonality, and the idea is to use that to try to find the cause-effect relations, right? To try to find the commonality.
Okay, thanks for making this clear.
And
Go ahead.
if you are concerned with the deep learning problem, right? because if you are working in images, we can't do cause effect relations on the pixels, right? You can imagine doing this on the low dimensional embedding space. So you try to find the causal factors and do the causal graph there, and not necessarily on the pixels.
Yeah, but then you have the problem that you cannot interpret the features, right? Because they are embeddings and not your input features, right?
But the goal here is you might not interpret it. That's you still have that problem. But if the features are causal, you know that if there are distribution shifts, the knowledge that you have from the causal factorization will still help you with the problems I said before, right? Either for the fine tuning or the having just a model that is better when there are mechanism shifts.
Okay, yeah, makes sense. Thank you. So we have 2 questions already in the chat, so I'll post it here. The first one is, what is the most common use of causality in deep learning? Is it doing interventions, observe the differences and extract cause-effect relations, or having a data set without interventions?
So there are lots of work in deep learning with causality, which is related with counterfactual fairness. So they try to ensure that your model, when you sort of go to the data set and let's say switch the gender, that outcome for some target, let's say giving a loan or something like that, shouldn't change. And that is inherently a causal idea, because we aren't conditioning, right? We are changing the system. So we assume that the curriculum is the same. You only change the gender. But there might be possible that curriculum with the gender maybe not a good example, but you hypothetically could imagine that curriculum wouldn't appear exactly equal if you had the different gender. Because this example is not good. But so essentially, when you do an intervention, you might get data that actually doesn't exist, hypothetically. And this is inherently a causal concept. So counterfactual fairness is one. There are many. Also in this case, I showed you a lot about using deep learning to try to find causality, but there's also the opposite, right? And also the thing I said with deep learning about trying to find causal representation learning. So trying to find the low dimensional embedding space that retains some cause effect relations, where you assume that your data, let's say the images, are a transformation of the samples from a structural causal model. In that sense, that's also similar with the deep learning.
Thank you, Gonçalo. And we have another question from Luis. Luis asks, can you explain how this relates to energy-based models? I see a lot of similarities.
I mean, energy-based models is just, from my understanding, I like the topic. So it's just a way to define, to learn an intelligent system, right? So the idea is that a prediction should be the minimization of an energy function, let's say, in a simple way. So I guess one thing is like tools for fitting conditional distributions or functions. Another thing is just causality. So causality, we are essentially adding these intervention ideas and things like that. But in the end, we will want to find functions, and in that way, we can use energy-based models for that. So I guess there's not necessarily related. So you can use energy-based models with causality, but not necessarily in terms of concepts related.
Thank you, Gonçalo. One other question that I had is, like you mentioned, because you mentioned Udea Pearl, I remember reading in his book the 3 letters, the letter of causation. And the first is statistics, the second is intervention, that I think is what you talked about, and the third is counterfactuals. So is your work in the second letter of causation?
I mean, my work is sort of trying to figure out the structure. And with the structure, you can also, if you know the structure, the graph, you can also do counterfaction, and if you know the structure and the mechanisms, so you have sort of a model for the mechanisms, you can do counterfactuals, right? So the idea here is like actually to to try to find the structure, and with the structure, hopefully, we can do the entire ladder, let's say. So yeah. So because if you know the graph, you can do counterfactuals, right? The issue here is actually finding the graph such that you can do counterfactuals.
Yeah. Okay, yeah, makes sense. Yeah, so maybe before we finish, I just would like to know, like, what are your thoughts on the near future of a causality in deep learning? Where do you see this field going in the next applications?
I see lots of I know of lots of work that are trying to do causal discovery. So because this is for many problems in science, trying to understand cause-effect relations is really costly. They have to spend lots of money in trying to find participants to try to understand the cause-effect relation. So causal discovery is really important, and in that way, deep learning has a lot to give to causality in general. But also, there's like the other way around, where people are trying to solve problems from deep learning with causality. And one of the approaches is what the thing I already said, which is causal representation learning, where we're trying to find these special causal factors, which are these distinct modules of information that we can gather from unstructured data, and ideally we could use this to make counterfactuals, in the sense that we can make an image. I know that there's already work that does this without causality, but you can like sort of make an image where you force, like let's say a person that never heard an ad, and you have a picture and you want just force her to add an ad, where an ad. So doing those types of manipulations in text as well, and in general, and also deal with these issues of distribution shifts and robustness, where you want your models to still be good, just even though you deployed your model and it already changed the system and the data generating process, you still want it to perform well. So
yeah, makes sense. Okay, thank you. We have a new question in the chat. Francisco asks, related to causal representation learning, how limited might be our solution if we don't know the entire causal structure that generates the specific observation? Is an abstract version enough?
I guess this field is still super ambiguous, right? Because you can have like many layers of what is causal, right, and many layers of abstractions to connect, right? And the idea is that generally we'll have to make assumptions, especially surrounding sparseness, where we assume that the graph has few edges, so the graph shouldn't be too bushy, in the sense that there's like lots of arrows, just a few, and with those types of assumptions, we might be able to guarantee that we are actually able to recover the true underlying graph. And I guess that's what I have to tell about this question. So there's still too much ambiguity in this case. So we have to make like the objective of what even means to have causal representation learning more concrete, and then make methods around it, right?
Yeah. Okay.
Because
thank you.
yeah,
I
because
don't know if you want to add more. Go ahead.
Sorry. Yeah, but because in general it will be, if you are doing unstructured problems, video images, you will never have the structure entirely, right? The best thing you can hope for is an abstract representation of the causal graph on some meaningful variables.
Yeah, thank you, Gonçalo. I think we are all out of questions. Thank you so much for your presentation and for answering all of our questions, and congratulations on your thesis. Yeah, just a big thank you, and thank you for everyone that joined. Please fill our feedback form that's in the video's description so that we can improve our meetups. And I guess I see you all next time. Bye-bye.